Alright, so for number 61, we have a racing car completing a lap around a circular track in 14.3 seconds. So let's draw our track. It's got a radius of 50 meters, and the car is moving at constant speed. And the first thing they ask for is what is the car's acceleration. Now, that kind of sounds like a trick question given the fact that it's moving at constant speed. But remember, if we're moving around the circle, we're constantly changing direction, so therefore we have an acceleration in the form of centripetal acceleration. So remember, our formula for centripetal acceleration is v squared over r, and in this case our velocity is going to have to be found using our formula distance over time, because we aren't given a straight velocity. We know that the distance around the track we'll have to find knowing the perimeter of a circle, and the time is given to us as 14.3 seconds. So one lap, remember the circumference of a circle is 2 pi r. So therefore the circumference of this circle is going to be 2 pi times 50, which will be 314 meters. So that's also going to be the distance we travel in that 14.3 seconds. So we go 314 meters in 14.3 seconds. That is going to give us a speed of 21.9, or actually 22 meters per second. Now, again, acceleration in this case is v squared over r. So my acceleration is going to be 22 squared over the radius 50, and that is going to give me 9.6 meters per second squared. Now from this point, we want to find the centripetal force. Remember, just like any force, mass times acceleration, but centripetal force is going to be mass times centripetal acceleration, which our mass is 615 kilograms. Our centripetal acceleration is 9.6 meters per second squared. Multiplying those two together, I'm going to get 5,930, 3 sig figs, which I should add a sig fig up here, 5,930 newtons. Alright, so for number 62, we have a hammer throw with a 7 kilogram hammer. So that's our mass. The axis here is going to be the hammer from the axis of rotation looks like it's going to be 1.8 meters, meaning this distance right here is 1.8. So my radius is going to be 1.8 meters. And if the hammer makes one full revolution in 1 second, what is the centripetal acceleration of the hammer? Now, one way we can write that time, we can consider that the time period with a capital T of 1.0 second, meaning that completes one cycle or one complete revolution in 1 second. We'll be talking a little bit more about time periods later on in the course, but basically that's saying that it will complete that circumference, which is 2 pi r, in that time period. So our circumference is going to be 2 times pi times our radius, which is 1.8, and that's going to give us a total distance of 11.3 meters. And since it's going a distance of 11.3 meters in 1 second, that means my velocity is going to be 11.3 over 1.0. I should make this a capital T, which is 11.3 meters per second. So my centripetal acceleration, remember, is v squared over r, and my v is 11.3. Let's square that and put it over my radius, which is 1.8. I get an answer of 71 meters per second squared. Now we want to know the tension in the chain. Remember, the tension is acting as our centripetal force here, keeping it in the circle. And centripetal force is simply given as mass times your centripetal acceleration. So that tension is going to be mass, which is 7 times centripetal acceleration we just found as 71, and we're going to get 497 with sig figs. That would be look like it'd be 500 newtons. Alright, so for problem 63, we have a coin placed on a vinyl stereo record that's making 33 1/3 revolutions every 1 minute. So in other words, it's rotating 33 1/3 times each minute. So I'm going to call my time 1 minute or 60 seconds. And the distance we're going to find out in a minute here that it rotates. The first thing they're asking though is in what direction is the acceleration of the coin. So again, the coin is wanting to go off in a tangential direction due to its inertia, but the friction between the vinyl record and the coin is going to keep it in the center, or I'm sorry, moving toward the center at all times, keeping that circular motion. So the direction is, again, as we've seen in previous problems, toward the center of the record. For part B, finding the magnitude of the acceleration when the coin is placed at these 3 different radii. So the first radius we have here is 5.0 centimeters. So I'm going to write radius is equal to 5.0 centimeters, or 0.05 meters. So my distance is going to be that distance it travels in 60 seconds. So how we're going to have to find that is it goes around 2 pi r times for 1 revolution. 33 1/3 revolutions is going to be a distance of 33 1/3 times that circumference. So then my distance ends up being 10.4 if you multiply that all out, or 10.5 meters, meaning it's after it goes around 33 times, it travels a total distance of 10.5 meters if you were to stretch that all out in a straight line. So the velocity is going to be that distance over time, which is 10.5 meters in 60 seconds, giving us a speed of 0.17 meters per second. Seems like a reasonable speed for a record to be rotating. Now, that's not our acceleration though. The acceleration is going to be v squared over r, which is 0.17 squared over 0.05 for the 5 centimeters, and we're going to get 0.61 meters per second squared. Now it's the same process for finding the centripetal acceleration at 10 meters and at 15 meters. We just have a radius of 10 centimeters, which is a tenth of a meter, and we also have 15 centimeters, which is 0.15 meters. So we're just going to toss in for our radius here, we're going to toss in 0.10, and we get 20.94 for our new distance. And when we plug that in down below, it's going to give us 0.35 for our velocity, 0.35 meters per second. And we're just going to go ahead and put that back into our centripetal acceleration equation over here, v squared over r, which is going to be 0.35 squared over 10, and that's going to give us 1.22 meters per second squared. Now I'm not going to go through the process for the 15 centimeter radius, but when you plug that in the same way, you should end up getting a centripetal acceleration of 1.83 meters per second squared. Now let's go on to answer part C. What force accelerates the coin? They're asking about centripetal force, or simply the friction that's keeping the coin on the table. Since we don't know the mass, they're not asking us to solve it. What they really want to know is just that friction is what's acting as a centripetal force. For part D, they're asking which of the 3 radii would the coin most likely be flying off the turntable, and why. And I guess you just have to think of this as which scenario would the turntable have a harder time holding on to the coin. The coin has the highest acceleration at the 15 centimeter mark. Centripetal force is going to increase with acceleration, so it would take a lot more force to keep that coin on the turntable with this higher acceleration. So our answer is going to be with the 15 centimeter radius. That's going to be the hardest to keep on the turntable.